How's it going, guys? White Rabbit here. A few days ago, I had an interview with Reds Rhetoric. You may recognize that name because I've mentioned it in a couple recent videos. He appeared on a podcast called the Round Earth Skeptic Roundtable. And on that podcast, he was defending the heliocentric model. More importantly, he was debunking the flat Earth model. I thought he did such a wonderful job explaining the validity of the globe model and why it is, in fact, a reality, that I wanted to invite him onto my channel to share much of the same information and to kind of pick his brain a little bit. Now, this may sound a little unusual for me to invite onto my channel someone who is so adamant about the heliocentric model, especially considering the fact that I have put out a few different videos talking about the validity in the geocentric model. And I want you guys to understand, first off, I am neither a geocentrist nor a heliocentrist. I see validity in both models. I think both models work, and that's part of the beauty of it. But more importantly than that, if you don't fully understand the heliocentric model, or any other topic that you're debating against for that matter, then you have no business debating the issue at all. And I've seen perpetuated throughout the truther community as of late, people going after various different commonly accepted models and theories where the majority of the cases made against the accepted model are based on a misunderstanding of what the model actually says, or the explanation for whatever it is they're arguing against. And it's important, if you are truly in pursuit of the truth, you have to research all sides and all perspectives. You can't just make up your mind based on one thing and ignore the other topics. That is being willfully ignorant. Now, there were several things that Reds Rhetoric brought up in this interview with him that can also be explained with the geocentric model. And I apologize if I sound lethargic throughout this entire interview. I had a very long day and I was just trying to get through this interview because it was really the only time I had to do it. And in that, I didn't really take advantage of some of the points that he brought up to explain how some of the points that he brought up can be explained in the geocentric model. But regardless, that wasn't really the point of the interview. Okay, the point of the interview was for you guys to hear the heliocentric model explained by somebody who knows what they're talking about. Now, I could have gone in later here in the post-edit and added the legitimate explanation for some of the points that he brought up in the geocentric model, but I decided against doing that specifically because it wouldn't be fair to him. For one, I didn't tell him that I was going to do that, and for two, it's not giving him the opportunity to respond. So instead, I'm just going to play the interview more or less how it was, let you guys listen to his perspective on things, allow him to explain the globe model and the heliocentric model, and leave it at that. The other point that I want to bring up is that Reds Rhetoric is not a truther. I'm pretty sure he's an atheist, although I'm not 100% on that. He's pretty much a polar opposite of me and my channel. In fact, really the only thing that we have in common at this point that I've noticed is that we're both trying to push what we hold to be true. And we're trying to defend that truth. And on that basis and on that ground, I respect the guy. But I wanted to bring this up because many of you, if you were to go to his channel, would be very offended by some of the things on his channel. For example, he's made various different videos going after creationists and defending the theory of evolution, which, as you guys know, is something that I boldly disagree with. And there are various other things like that he covers on his channel. But again, you know, this is a point of examining all perspectives, okay? If you're truly in pursuit of the truth and dedicated to the truth and to good, solid research, you have to be willing to set aside your biases from time to time to examine the alternative arguments. And just one last thing, in the description section down below, you will find links to various things that he discussed throughout this interview, and to the slides that he was using and some slides that he wasn't able to use. So if you would like to follow along with some of the things that he's talking about, make sure you click on those links and check out the slides presented. So without further ado, here's the interview. How's it going, guys? White Rabbit here. Today I am joined with a special guest, Reds Rhetoric. I've posted a couple videos recently about Reds Rhetoric most recent appearance on the Ball Earth Skeptic podcast, where he made a brilliant presentation on the globe model and why it is a reliable model and why you can take it as a credible alternative or a credible model as opposed to the ludicrous flat Earth model. So I reached out to Reds Rhetoric and I invited him to come on the show and basically go over a lot of the things that he went over in that podcast here on my channel. And without further ado, let's jump right into it. Reds Rhetoric, how are you doing, buddy?
I'm doing well. Thank you very much for having me.
Thanks for joining. Appreciate it. So, where do you want to start off with this?
Well, I guess I could, give a little bit of an introduction and then I can jump right into it if that's okay with you.
Perfect.
All right, sounds good. So again, my name is Red. I run the YouTube channel Reds Rhetoric, and I promised for White Rabbit's sake that I would keep this PG. So you may know me for cussing a lot, but I will do everything I can to not cuss once throughout this entire broadcast. So you're going to see kind of the happier side of Red. But I figured that I would go in and just run down exactly what I went over on that podcast, because I was kind of going through it a little bit fast and just jumping through slides. So I figure slow it down, break it down into little tiny bite-sized pieces, and that should make it easier to understand.
Great.
All right, perfect. So with that, I'll go ahead and share my screen. So bear with me for a quick moment.
Okay.
There we go. So we should be seeing my screen right about now. Let me hide that real quick. All right, so let me know if you got a visual.
Yep, I got you.
All right, perfect. So let me first go over something known as parallax and how we can use parallax to find the distance to distant objects. So let's say we had 3 soda cans, one at each corner. You should see my mouse moving there. So we had a soda can here, we had a soda can here, and we had a soda can here. And we measured the distance between these 2 soda cans. We measured the angle at which they were seeing this soda can. With this simple equation, you can find the distance of x. And when we actually do this in real life, we see that if we were to actually measure, like with a tape measure or something, the distance from here to here, we see it matches perfectly with this equation. Now, what this shows is that this method, this parallax method, is a reliable way to find the distance to objects. And, this is exactly why objects closer to you appear to be moving faster than farther ones. It's because of parallax. So it's a good tool to use. And so to go over the equation, it's the baseline, which is your known distance between the 2 observers, tan, which is just a tangent rule. You can find it on any scientific calculator. Theta. Now, theta is just the parallax angle. You can represent theta with A, B, C, any arbitrary letter. Just as long as you give it the correct value, your equation is going to work out. So let me go ahead and just go over something real quick. So basically, we can use parallax to find the distance to one of our neighbors, which is Venus. And this was actually done as recently as 2012, I believe it was. Thunderfoot actually made a video where Venus went in front of the sun. And depending on where you were on the planet, you could actually see Venus go across the sun at different spots. So, for example, let's say you were on the top side of this Earth model right here. You would see Venus transiting the bottom part of the sun. If you were on this side of the Earth, you see it on the exact opposite side. And since the angle of, or the angular size of the sun is known, it's about 30 arc minutes, you can actually get a degree between these 2 points. So if you were to take notes of exactly where you saw it and compare notes with another observer, you can find your parallax value. And if you were to simply figure out the baseline between your two observers, you can actually make a parallax measurement to find the distance to Venus. So why is this important? Because one of the questions that was asked on the podcast was, how do you know how far away the sun is? And how do you know we're going so fast around it? And this is important to answering that question. So with the baseline no, you can use Google Earth. Now, of course, some people will say, oh, you're presupposing that Google Earth is accurate. Quite honestly, it has never gotten it wrong with me before. So I can trust that Google Earth is accurate. If you're going to assert that Google Earth is not accurate, that is your burden to bear. But anyway, let's go ahead and continue. So we can, by knowing where Venus transited across the surface of the sun from the viewpoint of our two observers, we can get the angle of B, which is equal to the angle of A. So A equals B. All right, let's move on. Which means we can now do a little bit of trigonometry and find the distance to Venus. So on this side, I just did a little bit more complicated version of this equation, which is a simpler equation to use. So if you're going to figure out parallax, I recommend using this equation, but whatever. Anyway, once you actually go through the equation, you find the value to Venus. You find the distance to Venus. And it comes out to 4.5 times 10 to 7 kilometers, or in other words, 45 million kilometers. And if we were to do the same thing to this side, which is the simpler formula, we see that it roughly equals the same amount. So with this observation, we found the distance to Venus. Now at this point, I pointed something out. If Venus is going in front of the sun, and Venus is 45 million kilometers away, that already puts a nail in the coffin for the assertion that the sun is only 3,000 miles away, because the sun obviously has to be further than Venus in order for Venus to go between it and us. So that kind of puts a nail in the coffin for this 3,000 mile away sun assertion. So if we were to continue, we can use Kepler's third law to help us even further. Now, what is Kepler's third law? Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. I know that is a lot to take in. None of you guys probably understood what I just said, so I'm going to break it down. And basically, let's give you some numbers. So in the top corner right here, that is basically Kepler's third law. P to the second equals a third. So basically, all we have to do is take the orbital period, which we know from observations is 0.616 years. So it takes Venus 0.616 years to go around the sun once. Now, because we know how long it takes, that is directly proportional to how far it is away, which means it's 0.3 cube third. See how that works? That'll give us 0.7 astronomical units. If we're using ourselves as the standard, Venus is 0.7 of the way there out of 1. So we know the Earth-Sun distance is going to be our standard, 1 astronomical unit. 1 astronomical unit, as of right now, is not known to us. We don't know what it is. However, Kepler's third law states that Venus is 0.7 astronomical units away from the sun, which means that by simply subtracting 1 from 0.7, or simply subtracting 0.7 from 1, we can find the distance from Earth to Venus. And it turns out it's 0.3 astronomical units. Now, this is great because we already found the Earth to Venus distance. Remember, it was 45 million kilometers or so. So that basically, as a consequence, means that 0.3 astronomical units equals 45 million kilometers. This opens a lot of doors for us. This actually allows us to find the distance from Earth to Sun, the value of the astronomical unit. So if we're moving forward, all we have to do is find out how many times 0.3 goes into 1 astronomical units. That will construct a ratio. And it goes into 1 astronomical units 3.333 times. So all we have to do to find the distance to the sun from Earth is simply multiply our known distance to Venus by this ratio, and we get the value of the astronomical unit, which is 15 times 10 to 7 kilometers, or about 150 million kilometers or so, which is exactly what they, the nameless they, have been teaching us the entire time. They weren't lying about this. And this can be easily confirmed through observations that you can do yourself. You don't even have to use Venus. You can use Mercury when it transits across the sun. Now, moving on, because we know the distance to the sun now, we can find the circumference of our orbit, and this is presupposing that we are going around the sun. So let's go ahead and find the circumference of our orbit. Well, since we now know what 1 AU is, which is our radius, we simply times that by 2 pi. That will give us our circumference. And you've probably done this in school. Finding the circumference of a circle is pretty standard stuff. But I went ahead and did the math, and it comes out to 942,477,796 kilometers. That is how many miles in circumference our orbit is. Now, since we know how many hours there are in a year, and the definition of a year is one trip around the sun, we can see how fast we're actually going. So we have distance and we have time. Speed is distance over time. So some simple division gives us our answer. And the answer is 107,515 kilometers per hour. And if we were to convert that to miles per hour for all my American brothers and sisters out there, we see that it's 67,196 miles per hour. That is the speed we are traveling in our orbit. And at this point, I would like to ask Mr. Rabbit, is there anything that you would like for me to elaborate on?
Couple questions. Number one, does it matter that the Earth's orbit is not a perfect circle?
It does not matter because we're simply taking the average.
Okay. And number two, when you were figuring out the distance back several slides of your baseline, did you account for the curvature of the Earth?
I did not account for the curvature of the Earth. I simply used the distance between our two observers, and they were more or less on a flat plane. It was a distance between me and California, roughly, and then you simply add that to Hawaii. And the way that we did it is that we already know the angular size of the sun, so the curvature can be negated since that is a constant. So we don't need to take the curvature in account at all.
Okay.
That's all. Perfect. So basically, we move on from there. But I do want to say one more thing when it comes to the baseline. So the baseline, again, is, just a straight line from one point to another. It's the shortest distance. Now, if you were to think of the curve, if it makes the baseline a little bit longer, sure, that might skew the results, but it's not going to skew it that much. You're still talking about several thousand miles of baseline to work with. And so if you have a slightly longer baseline, that might make your parallax value a little bit less. So actually, taking into account the curvature of the Earth would not be helping the flat earthers' case. In fact, you could say that it would only be hindering it, because even if you gave them that handicap, the sun would still have to be further away than 3,000 miles by such an astronomical magnitude that it makes the flat earth concept absolutely ridiculous. So they can give it any handicap they want. And even on their flat earth model, the baseline between our two observers would almost be equal to the baseline that I used in this example. So they still don't save themselves there.
All right.
Perfect. So we'll go ahead and move on, because another thing they asked me on that podcast was, how do you know that we are the ones that are spinning? Why isn't the universe around us whizzing around us? How do you know that we are actually the ones spinning on our axis? So they asked me that question. So I started figuring out, okay, let's go ahead and answer that question. And I think I have some mathematics that prove it. And I'm going to try and explain it in a different way than what I did on the podcast. So the first thing we need to accept is that there is a force holding all things to the Earth if the Earth is really the center of the universe. So whatever that force is, I said on the podcast, you could call it Chuck E. Cheese. it doesn't matter. It doesn't matter if it's gravity. It doesn't matter if there's a physical a string attaching on the planets to us. It doesn't matter if it's magnetism. It doesn't matter at all, because the strength of that force has to be proportional to how far it is away. It has to. Now, I'm going to explain it like this. Imagine you had a rope with a weight at the end of it. Now, let's say the rope is only about a foot long or so, and you twirl it above your head. To make that weight spin around your head 1 revolution per second, it doesn't take that much force at all. Does not. And that muscle, that strength, is the same strength that is holding the objects to the Earth. So if you twirl that weight above your head, it doesn't take that much strength to actually make it spin 1 revolution per second. However, if we were to extend the distance, extend that rope out to about maybe 10 to 15 feet, you'll find out it's a lot harder to get that weight in a complete circle to get that weight to go in a complete circle every second. You'll find you need to put a lot more force and a lot more strength into actually making it go faster so that it can complete its trip in 1 second. The same concept applies. The further you get away from an object that is the central force, the more strength you have to put on it, or the more force is needed to make it go around the Earth once every second. So we can actually use mathematics and find that out. Now, one thing that we did is that it was gravity. You may have to censor that out, by the way. So it was gravity that we are going to say is actually causing this, because, hey, it works for everything else, and it's actually been demonstrated and proven. Look up the Cavendish experiment. It'll go over it in more detail. But anyway, the Cavendish experiment gave us the value of big G, which was 6.67 times 10 to negative 11. And so you can use that to construct an equation to find how much force, gravity, is being generated by these two objects. So we have F equals big G, which is, again, the gravitational constant found by the Cavendish experiment, M1, M2, which are just our two masses. Now, you can switch the two. It doesn't matter so long as you don't double in them. Just assign one to M1, assign the other to M2. It works out over R to the second. And R is simply the distance between the center of the masses. This is a very simple equation, and if you go into any physics textbook, you're going to see this equation. It was made famous by Newton. And this equation allows us to calculate the force. So let's go ahead and find that out. So in order to find the force and to make our point, we need to first find the mass of the Earth. Now, the way we're going to do that is we're going to represent M1 with Neptune's mass, which was the object that was the example with the orbit around the Earth. So the reason we're going to do this is we're going to try and prove a point. We're going to try and prove that in order to find out the force, you don't even need to know the mass of Neptune. You don't need to know the mass of the Earth. You just need to know the distance to the object. So the way we're going to prove that is we're going to first construct an equation with our known values. So if we have a known value, we can go ahead and find the known force that will be needed, that Earth needs to exert on Neptune in order to keep it going around us at its distance every 24 hours, which it has to do in the geocentric universe. So the way we do this is that we have a body of mass, M2, which is Neptune, moving along a curved path of radius r. Again, that is the radius of its orbit, at a speed s, self-explanatory, where it completes the orbit in 1 day, which it has to in geocentric universe. That would be t. T would be in seconds. Now, how many seconds are there in a day? Well, about 86,164 seconds are in a day. So we know that. So now we can go ahead and construct our equation. That gives us F equals M2, which is, again, the mass of Neptune, times R, which is our radius, times s to the second. Now, let's go over what s to the second. That's 2 pi over t, as we just said. And to the second, that would make it 4 pi to the second over t to the second. Because all you do is multiply everything by 2, or multiply it by itself by 2. Very easy. That makes it this equation. F equals M2 times R, 4 pi to the second over t to the second. And when you plug in the values and you crunch it out, you get this outrageously big number. Now, Mr. Rabbit, do you want me to actually say what that number is?
Yeah.
Uh, okay, so deep breath, guys, deep breath. Well, it's 2 nonillion, 342 octillion, 889 septillion, 966 sextillion, 90 quintillion, 690 quadrillion, 602 trillion, 77 billion, 912 million, 164,935 newtons of force. Wow. Okay. Deep breath, guys. Deep breath. So that's how much force is needed to keep Neptune in a 24-hour orbit around us at its current distance. So why is this important? Well, we can go to the next slide and we can use this to find the mass of Earth. Now, exactly what we did last time is we simply plug in the values where they belong. And just to go over it one more time, that would be this equation right here. Since now we have the force in newtons, we can just fill in the gaps. And we get that Earth would have to weigh 6.354 times 10 to the 39 kilogram. That is a very big number, but the size need not concern us. Let's see if we can get that same exact answer without knowing the mass of Neptune, and only knowing the distance it is away from us and the time it takes to go around us. But, 4 pi, g, and t, they're all constants in the geocentric universe, which means r is the only non-constant, which means we can just simplify this equation a bit, make it easier to understand. When we do, we can actually find out exactly how much mass the Earth needs at a given distance in order for the object to go around us in a 24-hour period. Now, let's test to see if this equation gives us the same answer as this equation. Bam! Right there. 6.354 times 10 to the 39 kilogram, exactly what we had the last time. So this equation with the known value equals this equation with the unknown value. The unknown value of Neptune, the unknown value of the mass of Earth. What this means is that it doesn't matter what the mass of the object is. You just need to know how far it is away from us. It doesn't matter if Neptune is Jupiter. It doesn't matter if Neptune's made of cheese. It doesn't matter if Neptune is the size of a golf ball. It doesn't matter. This equation, therefore, is all we need. Now, I said that we could simplify it, so we will. When we simplify it, it equals 79.676 r to the third will equal the mass of the Earth. Now, what this shows is that the further you go away from the Earth, the bigger distance of your radius, Earth would have to be many different masses, aka exerting a completely different force for each individual object at the exact same time. Many different things at the exact same time is a possibility. You can't be do and you can't be don't at the exact same time. It's just an impossibility. What this shows is that in order to solve the problem, something's got to give. And the thing that gives is our fixed perspective. The way we solve it is we simply unfix the perspective. We let the Earth spin on its axis, and it solves all the problems because you're not breaking any rules at that point. You're not breaking the law of gravity. You're not saying that Earth has to be many different things all at the same time. John LeBon's on Skype. So basically what I'm saying is that the way we fix this issue is that we make the Earth spin, not the universe around us. And that was the presentation I gave. And I hope I was a little bit more clearer with this presentation. I try to be, but if you're confused on anything, I'll be more than happy to go over it again.
No, that was great. Let me ask you a question. An argument that I've heard geocentrists use while trying to explain the geocentric model with gravity is a gravitational void in which the Earth sits, wherein the entire universe and the gravitational forces throughout the entire universe kind of piggyback on each other to create, what it is that we see. So, in other words, instead of the Earth being solely responsible for the, you know, each individual varying gravitational force at any given distance, it's actually the entire universe working in conjunction with each other. Have you heard about that before?
Yes, I have. The gravitational void on Earth would basically render the Earth gravitationally free. And we know this is not the case. Otherwise, the Cavendish experiment would not work, since it is a tool that is designed to measure the gravitational force. And if Earth is in a special spot in the universe where there is a gravitational void, you would not have that experiment working the way it does. And we also use the equation by the value of big G to send satellites into space like Cassini, Voyager, New Horizons. They follow the same exact constant. And so if the same exact constant that was figured out on Earth works out there, then what is there is also what's right here on Earth, which is gravity. And that is why all these space missions that we have sent to other planets are so successful, is because we have pretty much solved what equations or what constants we need in order to figure out how to get from point A to point B.
Well, if there was a gravitational void, well, let me back up a second. We are dealing with the conspiracy community here. Keep that in mind.
Understood.
Okay. So low Earth orbit would be, I would say, acceptable reasoning within the conspiracy realm, but anything outside of Earth's orbit is questionable in this community. Now, in a gravitational void, that wouldn't necessarily mean that the Earth would be without gravity. The Earth could still be acting independently on its own gravity.
Mm.
So,
That's
how?
well, that's basically what we're saying. Earth does have its own gravity, but if it's in a gravitational void that negates gravity and Earth has its gravity, then by definition it would negate the Earth's gravity. And by negating the Earth's gravity, we would not have the ISS orbiting around us, and our moon would not be in the lovely orbit that it's currently in. Another thing that would happen is that the Lagrangian points that we have for the home of SOHO and the newly launched Discover satellite, which has beamed back amazing images of Earth. Conspiracy theorists have had fun with that one. They would not be present because you need the Earth's gravity for those Lagrangian points to even exist. And the reason that they exist is because there is a gravitational center, which is right where the Earth happens to be. Fancy that. So the way we would have to look at it is we're going to have to ask the question: what can Occam's razor do for me? And if the gravitational field is coming from the central point of the Earth, then I guess it's safe to say that it's the Earth itself that is generating the gravity field, and that it is in fact not negated after you go outside low Earth orbit.
Well, I guess what I'm saying is like if the void was outside of the Earth and the Moon, right? And the Earth and the Moon acted on their own gravitational forces, and the void encircled that area. Do you get what I'm saying?
Yeah, that's why the Lagrangian points are so good, because the Lagrangian points place them well outside of the moon's orbit. The Lagrangian 1 point, which I just mentioned recently, is currently home to SOHO and the Discover satellite. The Lagrangian 2 point, which is the point it's the point that is further away from the sun than we are, and it is also outside the orbit of the moon at roughly the same distance as it would be closer to the sun, on the sun-facing side of the Earth. And that's going to be the home of the James Webb Space Telescope. And the reason that they exist outside of the orbit of the moon is because there is no negation. You know, the gravity of the Earth extends very far, and we know it extends very far by the mere fact that these points exist. And if we were to also look at the Lagrangian 3, and 4, they are so far ahead of us that it would make sense that the gravitational sphere of influence, if you will, of the Earth extends far out. And so there doesn't seem to be any negation there, nor does there seem to be a barrier where the gravity field of Earth just stops or it becomes a closed system. It's really an external system acting on everything else, the same way that all the other bodies in our solar system do.
Interesting. I'll have to look more into that.
Mm-hmm.
Well, that's all I had. Proceed.
All right, perfect. Little backup with the Lagrangian points. The Lagrangian point, let me go with Lagrangian 2, which is again the night-facing side of Earth. It is a orbit where the satellite is always going to be on the night-facing side of the Earth, and that point is about 1 million miles away. And that point exists well outside the orbit of the moon, being only 235,000 miles away. And by the mere fact that those Lagrangian points exist, the fact that there's this butter zone in space where we can launch satellites and basically have them sit there, you can basically see that the sphere of influence of the Earth extends outward from the central point, meaning that the Earth is generating its own gravity, and it is in fact not a closed system within the Earth-Moon system. It actually extends further out, and it does tug on other bodies. And it reacts with other bodies, which allows us to have these Lagrangian points. I guess that's an easier way of saying what I just said previously. So my apologies if my first attempt was a little bit confusing.
I got you.
All right, perfect. I guess moving on, we can talk about the shape of the Earth. I don't have any slides for this, so I'm just going to stop sharing my screen.
Okay.
All right, then. So if you have any questions or if you want to just chat about the shape of the Earth, that was Ziller's presentation. Unfortunately, Ziller's not here. He kind of has a lot of stuff to do. Almost at the S word there. So he kind of has a lot of stuff to do, and I don't have his slides. And so, but I'm more than happy to go over some of the more popular arguments with the flat Earth community.
Okay. Well, I guess the first argument to be made is that the Earth is flat.
Yeah, it's a nice assertion. I'll go over one that I heard recently. There's a YouTuber on here by name of The Morgile, and he made a video where he asserts that the centrifugal force needed to keep us basically alive on Earth would be so massive and so crucial to our survival that if we were to then go to the North Pole, it would squash us like a bug. Now, I understand what he's saying, so let me see if I can explain it a different way. What he's saying that if you're standing at the equator, spinning on the Earth's axis at 1,000 miles an hour, the centrifugal force that is basically in balance with the gravitational force would be at a comfortable equilibrium. But that equilibrium, you basically have a play of two very strong forces that if you were to go to the North Pole and negate one of those forces, since it is so crucial to keeping you basically feeling comfortable, so crucial to fighting against the pull of gravity so that you're not crushed by gravity, that by simply negating that spin, you would be squashed like a bug. And with that, do you understand the argument that he's trying to make, or should I try explaining it again? I'm terrible at explaining flat earther arguments.
I think I got you.
All right, perfect. So basically he's saying the centrifugal force at the equator is so crucial to fighting against gravity that if it wasn't there, you'd be squashed like a bug. So that's basically his argument in a nutshell. Now, we could actually debunk this with just two equations. Now, I understand that I don't have any slides in this case, so I will, for the sake of simplicity, send Rabbit some slides later on so that he can put them in post, if that's okay with him.
Perfect.
Perfect. All right then. So you only need to know two equations to solve this issue and basically see if it's actually an issue or not. Now, the first equation you need to know is basically the gravitational constant equation, which we saw previously, on our slides. And I'll be more than happy to just show that real quick. There we go. So this is the first equation you need, the gravitational constant. So what you need to do is plug in the value of g, which we already know, plug in the value of the Earth, and plug in the value of u, standing on the Earth, and the distance between you and the center of the Earth. That's all you need to do to figure out the force in newtons pulling you towards the center of the Earth, holding you to the planet. That is the amount of force holding you against floating off into space. So just finding gravity alone, we plug in our equations, and I'll give you the values. If we were to type in m1, which will say is the mass of the Earth, it's 5.9 times 10 to the 24. That's how many kilos the Earth is. I know, very heavy. Now let's substitute my mass. I'm about maybe 70 kilos or so. That's about, what would we say, about 150 pounds, I think that is. I think that's about 150 pounds. So about 70 kilos. We'll use kilos for this. And then we have the distance from us to the center of the Earth in meters. That's 6.371 million meters. That is the distance from us to the center of the Earth. So when we plug in all these values and we crunch out the equation, I don't know if I said the value of g, but again, it's 6.67 times 10 to negative 11. So 0.00000, you get the idea. But basically, you plug in those values, crunched out, and we find the force in newtons that gravity is exerting on you right now to hold you to the Earth. And it comes out to 678 newtons of force. That is how much force is holding you to the planet by its own gravity. Now, what we're going to do is we're going to find the value of the centrifugal force trying to throw you off the planet at the equator, again, which is spinning at 1,000 miles an hour. Now, the equation that we're going to use to figure that out is just a variation of the speed equation that we used earlier, which I will fast forward to right now. It's basically using this to find speed, 2 pi over t. So that's good. So we're going to have a variation of this force. And the variation, instead of plugging in these values, we're going to plug in a different value. F equals m2 times r, 4 pi to second over t to second. M2 is your mass, which for the sake of this example is about 70 kilos or so. R is the distance between you and the center of the Earth, which we already know, by the way, being it's about 6.371 million meters from you to the center of the Earth. That's the distance between you and the center of the Earth. So you simply crunch out the equation, and you can find out how much force is being exerted on you via the centrifugal force of the spinning Earth, which is, again, spinning at the equator at 1,000 miles an hour. And we find that if we were to solve the equation, where t equals a 24-hour period, aka 86,400 seconds or so, we find that the force exerted on you centrifugally is equal to 2.35 newtons, aka only 0.3% the strength of gravity, which means that if you were to go to the North Pole, you would not be crushed. You would weigh more, but you would only weigh more by 0.3%. You would weigh 0.3% more than what you would at the equator. So there's not really a crushing force there.
Has that ever been tested?
This actually has been tested. And in fact, Vsauce has a video. I don't know what the title of the video is, but I'll find it for you so you can put it in the description of this podcast if you would like. But he actually talks about a person standing at the equator and then going to the North Pole, and then the difference between it. And he gives some examples about how this was calculated. I'll get you that video. But the math works out, and what do you know? It works in reality.
I think something that might be beneficial for you to explain to the listening audience, because I hear this argument so much, and it makes my head hurt because I don't understand when people argue against something with such, you know, volition, uh, or with such vigor. When they argue against something that they don't understand. And so, what I would like to for you to explain is the argument that if the Earth is spinning at 1,000 miles an hour and you jump up in the air, you would land in a different spot.
I see. All right, yeah, that one is an argument made very popular by a YouTube user by name of Jeranism. Of course, I call him Jeranism just to be a little irritating to him. But he does make that point or that argument, and this is the same type of argument used for airplanes. You know, why can't an airplane lift off, hover, wait for the spinning Earth, and then land in a totally different spot? The reason being is that there's two things working against that. One is the speed of the atmosphere, which planes push off of, and the speed of the atmosphere is equaled to the ground speed. Relative to the ground, it's not moving at all. So you have a ratio of 1-to-1. And if you push against the atmosphere to go in a certain direction, you will cover just as much ground as you do in the air. So if the ratio is 1-to-1, that's almost like pushing off of the ground with your tires in the car and going to a different destination, and not being reliant on the spin of the Earth. Because not only is the atmosphere moving with the Earth, thus keeping the plane moving with the planet when it's stationary or not producing any thrust, not only that, but we also have Newton's first law. An object in motion will stay in motion unless acted upon by another force. So if we're already going 1,000 miles an hour and we jump up, we're not just going to suddenly stop. We're not just going to suddenly stop simply by jumping up in the air. You know this because if you're driving in a car and you can say, wow, relative to everything that's in the car, we're stationary, but relative to the ground, we're moving. And if you were to have a tennis ball with your passenger who's in the passenger seat going 70 miles an hour, and you toss that ball in the air, it's going to come right back down to his hand. The only time that's ever going to change is if that ball is tossed while at the same time your friend slams on the brakes. And now you lost the ball, and then you're going to have to pick up your teeth, which are now firmly implanted in the dashboard.
Yep.
That's basically what it is. So you have two things. Again, it's the speed of the atmosphere, which moves with the spinning Earth. So if an airplane puts thrust against that mass of Earth, which is again going in a 1-to-1 ratio with the ground speed, that means that, of course, it is the case that flight times between Tampa and Los Angeles, and therefore Los Angeles to Tampa on the way back, are the same, regardless what the spin of the Earth is doing, so long as the atmosphere is at the same speed as the ground. Relative to the ground, the atmosphere is not moving. And if you're pushing off of the atmosphere to get to places, of course, your time travels are not going to change simply based on which direction you're going. Because relative to the ground and relative to the atmosphere, if you're stationary, you're not moving. And the only time you would be moving is if you produce thrust, and you'll be moving against that area, you'll be moving against the atmosphere at a 1-to-1 ratio with the ground. So it's quite easy to picture. I'm just explaining it very poorly, I think.
No, that was great. I was actually hoping that you would use the car analogy.
Perfect.
Some flat earthers take it one step further, though, and I was mentioning this to you, I think, before we got on here. Taking that concept and applying it to rockets and spacecraft that launch up into orbit. And once they are outside of Earth's atmosphere, wouldn't they be ripped to shreds? Shreds.
Yeah, to shreds. Yeah, I get what you're saying. No, they would not be, because the thing is that when you're outside of Earth's atmosphere, you no longer have any drag going against you. And no drag means no friction, which means no pressure. Rockets go through this step in launching. It's called max Q. Max Q means maximum dynamic pressure on the vehicle, and that happens close to the surface of the Earth, maybe about a mile or two up. When it's got some speed, got some velocity to it, it goes through max Q, or maximum dynamic pressure. After it hits maximum dynamic pressure, that's just it. That's its maximum. It's downhill from there. So the higher it goes, the less overall pressure and less drag you have on the rocket, which means you're not going to have the rocket simply ripping itself to shreds simply because it has a lot of drag. The atmosphere gets thinner and thinner and thinner the higher up you go, until eventually you're essentially in a vacuum. And so no pressure, no dynamic pressure on the vehicle.
Excellent. Just on a side question, don't rockets normally take off in a certain trajectory that makes them like at a certain angle?
It's a yeah, well, they launch in a certain direction, and the direction that they actually go to is they head in the same direction that the Earth is spinning. The reason why they do that is because they can piggyback off of that already accumulated momentum, and it makes their launches more fuel efficient. Whereas if they were to go in the exact opposite direction that the Earth is spinning, you basically have a handicap. So they would have to first make up that handicap. They would have to accelerate an additional 1,000 miles an hour, and then keep going further on from there until they hit orbital velocity, which at about 255 miles up or so is about 4.7 miles per second, or 17,500 miles per hour. So if you were to go in the same direction that Earth is spinning, you only have to accelerate, like, let's say 1,000 miles an hour less. Where if you were to go against the spin of the Earth, you would have to make up that extra 1,000, make up that handicap before you actually hit orbital velocity.
That's also part of the reason why launch sites are further south, isn't it?
Yeah, that's why Cape Canaveral is a launch spaceport, because it's closer to the equator. The closer you are to the equator, the more efficient your rocket launches are going to be. And it follows the same concept as I mentioned previously, because the further you go towards the equator, the more speed you're going at, because the closer you get to the equator, the faster you go as it makes its revolution. So if you put a rocket launch site right at the equator, that is going to be the most efficient point to launch a rocket, as long as you're launching in the same direction that the Earth is spinning. Otherwise, that would be the biggest handicap you could possibly do if you're going in the opposite direction. So it's a double-edged sword.
Very good. If you don't mind, I'd like to kind of shift gears a little bit and delve a little into the geometry, basic geometry, as to how we can be certain that the Earth is a sphere.
Oh, most certainly. The one thing that I want to do is geometry, trigonometry, they're the same thing. You can actually correspond observations with the geometric findings and the geometric equations that we have. The geometric equations that we have correspond so perfectly to observations that that's how we know that they are factual. That's how we know that they are legitimate. And I'll give you an example. Recently, I posted a video titled Juranism Flat Wrong Part 3, where we go over the Chicago skyline mirage. And basically, we want to see if this mirage is within the capabilities of reality. We want to see what angle of shift does the light have to do to produce that mirage that was so far beyond the horizon that we could see basically 600 feet of the skyline. And so what we did is we took the accepted diameter of the Earth, and we also did a bunch of trigonomic functions to find the total arc degree that light would have to bend. And it turns out it was 0.12 degrees, which puts it in the realm of possibility. So it puts in the realm of possibility that this mirage is in fact possible on the round Earth. And another thing that we did to validate this was the Bedford level experiment, which a bunch of people like to use as sort of evidence for a flat Earth. But what was done after that was there was a professional observer that was took up his bet saying, okay, I can prove to you the Earth is round. He put 3 poles, one right next to him, one 3 miles out, and another one 6 miles out. And he aligned the first pole with the last one. And what he found is that the middle pole ticked up. It was rising. And then by seeing how much it ticked up, he could calculate what the average circumference of the Earth would be. And turns out it was, I think, within 1% of the accepted value as it is today. It was very spot on. So that's how we knew about it. In fact, Ziller has a blog post that goes into detail on how you can use trigonometry or geometry to find the total drop, how far under the horizon something would be, what the refraction index would be. And I'll actually go to that website, and I'll give you the link to that website so that you can see it yourself. All right, so just bear with me for a quick moment. This one, working with curvature, that's it. All right, so I'll go ahead and share my screen. So this is the website that Mari Ziller made, aka Hipster. He's gonna hate me for calling him that. I love you, man. Don't worry, no homo. But anyway, so we have basically a step-by-step description, a step-by-step instruction leaflet, if you will, on how to work with the Earth's curvature using trigonometry. And he goes into absolutely amazing detail here. And this is the same step-by-step process that we used in Juranism Flat Wrong Part 3. So if you want to see how this is done in action, I would recommend you go watch that video. Be warned, there's a lot of cussing involved. But you can go to this website, go through the step-by-step process, and it will give you all the answers you need. All you need to do is plug in the necessary values. And when you do, you will get the answer of y, you'll get the answer of t, and you basically have what each equation does and what it corresponds to. So it's basically like it's a problem solver for the curvature dilemma that a lot of flat earthers have, or a lot of people that are actually round earthers have, because they're like, this is actually stuff that I don't quite know. So I wish there was kind of like a step-by-step instruction booklet on how to work with this stuff. Well, there you go. Ziller went ahead and took care of all that hard work. And you can go to his website, which I will link right now to you, Mr. Rabbit, right there. And you can use his equations to find your answers. And this is a lot better than than Juranism's equation that was found in the book Zetetic Astronomy. I think that's what it was, by some author by name of Parallax. He calls himself Parallax, or Zetetic Methodology. I forget the exact name of the book. The word zetetic is in there somewhere. I just forgot the name of the book. But in that book, there's an equation that is supposed to be used to calculate the curvature of the Earth. That equation is only accurate to very small distances. I would not recommend it. And that equation will give you an error the further out you go. So for example, I wouldn't bother using that equation, which is something along the lines of, like, let's say we had, let's say we were trying to find the drop of 10 miles. It'll be something like 10 times 10 equals this divided by 12, and that will equal your drop. That is a very horrible equation to use. It would be much better if you used actual trigonometry, this one, via this page, which you can easily follow, and it will go over everything in excruciating detail, and you will get the correct answer.
Very good.
Perfect, perfect. And any other flat earther arguments that you have heard as of late?
Well, Ziller also went over something in that podcast as to if the sun really was 3,000 miles away, and was showing through, basic geometry how it wouldn't line up with observational data.
Yeah. Basically, one of Ziller's main point was angular size, and this is the actual law of perspective. And I'll see if I can find that, because I remember I actually made that diagram. Let me see if I can bring this up. Yeah, I do still have this diagram right here. So let me show you this diagram right here. This diagram is the actual angular size or law of perspective. This is the actual equation. A equals 2 arctan G over 2R. Now, what this means is that the further an object is, now these white bars right here, represented by the letter G, are all the same lengths. They're all the same lengths, they're just at different distances, obviously. And the further away this line, the further away G gets from the observer, the narrower, can't speak today, the more narrow the angular size of that object is going to look to us. And because the angular size of the sun is known and consistent, what this means is that the sun is roughly the same distance away from us throughout the day, or at least it's very far away where the shift is not noticeable. So what this shows is that if the sun were really close to us, going in its circular path as depicted on many flat Earth models, it kind of acts like a spotlight. What you would see is that it would start out further away from us at sunrise, get really close to us at midday, and then get farther away from us again at sunset. In order for that to match with reality, the angular size of the sun would actually have to change throughout the day. It would have to go from being very small in the morning to very large midday to very small again, roughly about the same size as it was in the morning at sunset. This doesn't happen. And you can prove this to yourself by simply taking some measurements of the sun. I would recommend using a polarizing filter, a million pairs of sunglasses. Do not damage your eyes. But if you find a way to just measure the angular size of the sun from morning to midday to sunset, you will see that the angular size does not change. And according to the flat Earth model, the angular size of the sun should be changing because it changes its distance away from us. Because as it's going around in a circle, it gets closer to a certain individual and then farther away. Then at the same time, it gets closer to another individual and then farther away. We should see the sun changing sizes. It doesn't do that.
Very good.
Yep. And the reason it doesn't do that primarily, and when all is said and done, it's primarily because the flat Earth model is wrong. Yeah. So that would be that one right there.
Well, what else did he cover in that video?
Well, let's see. One of the funniest ones I have heard, it basically goes over NASA is a hoax or whatever. Now, regardless what your opinion is of NASA, we have to agree on one thing. They know what they're doing. And one thing that they figured out is that rockets work in a vacuum. So one of the arguments that I've heard a flat earther say is that, oh, space travel is fake because rockets don't work in a vacuum. I'm still trying to wrap my head around that because basically every action has an equal and opposite reaction regardless if you're in the atmosphere or not. If you are spewing gas at such a high velocity at one end, you're going to be propelled forward, in the exact opposite direction. That is how rockets work. They basically follow that principle. Every action has an equal and opposite reaction. Basically, sit your tush down on a chair and hold a very heavy medicine ball. And make sure it's not one of those, actually, yes, make sure it's a rolling chair and make sure you're on a very smooth surface. I would prefer like a wood surface or a tile surface or something like that. And with this medicine ball, and don't break anything, throw it away from you forward as hard as you can. The medicine ball is going to get shot forward. However, you're also going to be shot back. Now, why is that? Is it because you were pushing against the air? Or was it because you were pushing against the medicine ball, the thing that you had contained only a second ago? It's the same thing. You lost mass when you threw that ball. The total mass between you and the medicine ball has been reduced because you just got rid of the medicine ball. That loss of mass transmitted or translated into motion. And the simple fact that rockets lose mass, a lot of it, I mean, after about 145 seconds or so, they lose over half of their weight in fuel, in rocket propellant. That's a lot of thrust. That is a lot of power. And that is a lot of equal and opposite reactions. Hence, rockets work. And it doesn't matter whether it's in a vacuum because the same law applies. Rockets work in space, guys. And if I had the money to build a rocket chamber, I would light off a firework just to prove it to you guys. But unfortunately, I don't have enough money for that. And I know that you guys, you flat earthers, aren't going to pay me enough to actually make one.
Well, while we're on the topic of NASA, since you brought it up, what are your thoughts?
Let's go down it. Let's do this.
What are your thoughts on the Van Allen belt?
The Van Allen belt is a wonderful argument that is made to basically argue against the fact that we have sent astronauts to the moon more than once. And they say that the radiation at the Van Allen belts are so deadly that it would kill any astronauts that try to go through it. This is wrong, and it has been demonstrated to be wrong by the mere fact that we actually went to the moon. Also, the amount of radiation that these astronauts would have been subject to when they went through the radiation belts would be equivalent to having 2 X-rays done. Now, Rabbit, let me ask you something. Have you ever had an X-ray in your life?
Yes, I have.
Okay, let me ask you. Do you remember bursting into flames?
Nope.
All right, and I can only assume by the mere fact that you're still here that you didn't die a horrible, horrible death.
I did not.
There we go. And another thing that's really funny that a lot of people don't want to mention is that they have no problem bringing up the Van Allen radiation belt, but what they don't ever bring up is Van Allen himself. Van Allen himself says that going through the belts is not impossible. Sure, he was a fan of fewer manned missions. He was a fan of more robotic missions to other bodies in our solar system. Okay, fine. That's perfectly okay. That does not mean that he thought that manned space travel was impossible. He was just a fan of fewer manned mission and more robotic missions. So be it, but that doesn't mean that he thought that manned exploration to the moon or eventually Mars is impossible. He definitely thought it was possible. He even says this himself. And I will give you a link in a bit to that quote where he says verbatim that manned missions to the moon are not impossible because of the Van Allen radiation belts, because of the belts named after me.
Well, there's a couple things I want to add. And I'm actually kind of surprised that you didn't bring this up. But one of the main arguments against the Van Allen belt radiation objection that, heliocentric and, people who think NASA are telling the truth, usually they use the argument that the astronauts flew essentially around the Van Allen belt, even though you know how the Van Allen belt kind of makes like a double horseshoe type of thing.
It's more like a torus, I think they call it.
Well, the point is,
like a donut kind of thing going on.
Yeah. Well, you have the inner belt and you have the outer belt, and they're both kind of like loops that kind of attach and are weaker at the poles and stronger, towards the middle of the radius of the Earth. The argument that is typically used for that is that the astronauts flew through essentially the weaker part of the belt so that they didn't have to endure as much radiation. So I'm surprised that you didn't bring that up. The other thing is that you bring up von Braun, but in that quote, von Braun also added, I believe it was the same quote, he elaborated and said that described that the mission to the moon would require a rocket essentially the size of the Empire State Building, and he suggested that there would be three of them to ensure success.
Yeah, oh, heard an echo there. All right. It's okay. Yeah, the idea was that they were struggling to find a way of getting astronauts to the moon as efficiently as possible. And the issue was is that they would not have enough fuel to launch back from the moon directly back to Earth. You know, if they were to go straight from the moon to the Earth and then not make a stop either way, which was the original plan. And that's why it was suggested instead that they already have a ship in orbit. Then all they would have to do is just have enough fuel to meet the ship that's already in orbit. And then they can simply dump the cargo, which sheds weight. And that less weight, less mass to carry means more efficiency. And that was a more efficient way of doing it. And the way that they were basically picturing it in their head is that the craft that they land is going to be so heavy and would require so much fuel to get back, one, to break free of the moon's sphere of influence, to gain enough speed to actually to get their translunar coast going through. It would take so much fuel, and they would have to carry so much weight that they would need multiple rockets to launch each one into a preliminary holding orbit, and then connect them all in orbit and then go to the moon. They found out to be hugely inefficient. And what von Braun didn't actually think of was, hey, let's actually just let's leave one craft in lunar orbit, which is exactly what was done. And let's only use the landing module to land and then get back to the ship that's already in orbit. And then we'll just simply dump it behind. We don't need it anymore. It's just extra weight that we don't need. So they make the craft lighter. They use less fuel, which means they didn't need a bigger rocket to get the job done. Now, sure, the Saturn V was a huge rocket. I mean, wow, it was big. But it would have been a lot worse had they not used that method.
Interesting.
Oh yeah, it would be a lot worse. In fact, you know, with they first thought about launching two rockets about the size of the Saturn V, simply because they didn't think about doing this method. They're like, okay, listen, I know this sucks, but we're gonna have to do it. We're gonna have to leave one guy on the ship, and he's not gonna walk on the moon. So Collins, I'm sorry, you drew the short straw. You're standing on the ship. I can just imagine how he was. Those lucky morons get to walk on the moon, and I'm stuck up here. I'm basically their taxi. Oh, welcome to Space Taxi. How can I help you? Yeah, I wish I could go walk on the moon.
Okay, so we've talked about as they go through the Van Allen belt and the amount of radiation that they would be exposed to.
And also talked about the size of the rockets, which is always fun.
Right. Have you done any research into the into plasma cosmology or the electric universe model?
I have not done any research into all those. This is actually the first time I'm hearing about these disciplines.
So you've never heard of them before?
Never heard of them before. This is the first time.
You should look into it, man. I bet it'd be right up your alley.
Be more than happy to. Just drop me a link, and I'll be sure to click on that.
Yeah, I've been doing a little bit of research. Well, I've been kind of watching what they put out for several months now, and they seem to have some pretty compelling arguments as to especially some of the formations that have been created on a lot of the different bodies, celestial bodies and things.
Mm-hmm.
And, kind of...
Yeah. I mainly keep my expertise within the solar system. As soon as you go outside that, things get a little bit complicated. So I'm usually like, okay, well, I'm out of my league here.
Well, I mean, like they explain various different things, like formations on Mars and like some of the trenches on Mars and things, and like some of the theories as to how some of those came to be, And they basically, some of that, well, for example, the Mars analogy, they explain it through a type of solar storm or a magnetic storm. And they also have an interesting theory as to star formation and various other things. It's pretty interesting stuff. You should check it out. I bet you'd like it.
Yeah, that's weird though, because star formation has pretty much already been solved. So they have a different theory of the accepted model, or
yeah, it's a contrary theory.
Contrary theory. All right.
It's kind of conspiratorial, but not really. It's just an opposing view.
I would hope it's not conspiratorial.
I know you're not the conspiracy type.
Nah, guilty as charged. I'm not a conspiracy type. Guilty as charged. I will hang that flag.
We'll win you over one of these days.
I welcome the challenge. Bring it on.
Yep. Well, did you have anything else to add as far as what we were discussing previously with the shape of the Earth and defending the heliocentric model and things?
Well, I guess finally, one of the big things that a person can do to prove that the Earth is indeed a sphere is simply take a trip to either Alaska, or you could take a trip to Antarctica. Yes, trips are offered there commercially, although they'll set you back a few $1,000s. They'll probably set you back maybe $20,000 or so. So yes, it is very expensive to get there, but I recommend going to northern Alaska. And in fact, you can land, in southern Alaska, maybe somewhere around Juneau, or you can go maybe near Pearl Harbor, or not Pearl Harbor. Yeah. Why did I say Pearl Harbor? Why did I say that? No, I don't want to say Anchorage is what I meant to say. Wow. Okay, so you can land in Anchorage, and you can drive up to northern Alaska while it's winter. Be sure you know what you're doing, otherwise you will get stuck, and you will be there for a while because no one's coming to get you. But what you're going to see is 24-hour darkness. 24-hour darkness. Now, if you were to come back 6 months later, you will see 24-hour sunlight. 24 hours. Look at the flat Earth model and try and twist reality in any way, shape, and or form to make that work. And then simply look at the globe tilted on its axis. Which do you think follows Occam's razor? Which do you think requires the least amount of assumptions? Which do you think follows the observations that we have done, given the angular size of the sun, ships disappearing over the horizon, the Bedford level experiment with the third pole rising, and given that in the southern hemisphere, the South Pole star is not the same as the North Star. The celestial, or the celestial center of our night sky is around Sigma Nautantis and not Polaris. So you have two central revolving points in the sky that are completely different from each other, spinning in completely different directions. How do you make that work on the flat Earth? Given that if you're at one side of the flat Earth and you look due south, you're going to see the same stars. Where if you look on the other side, if you're on the other side of the flat Earth and look due south, which is again to the outside edge, and you still see the same stars, yet you're both looking in the exact opposite direction. That is a contradiction. If a concept is self-contradictory, the concept does not work with reality, which means it's not reality. It's a fairy tale, and people are taking it up on faith, or based on the assumption that there's this huge, gigantic conspiracy where someone has a lot to gain, apparently, by simply lying about the shape of the Earth. I'm pretty sure that whatever scam that they're running they could run it easily well if the Earth was really flat.
Very good. Well, Red, it's been an absolute pleasure. I thank you for coming onto the show. I wanted to give you a platform to kind of go over a lot of the things that you went over in that podcast again, because I realize the emotional hostility that you must have been feeling going into that type of situation, and I also wanted you to have an opportunity to explain yourself without objection, and
Yeah.
so that people really get an idea of what it is that you are talking about.
Yeah. I understood what I was getting myself into with that show. I already knew that, and I'm just gonna be blunt here, they're intellectually dishonest. They really are in every sense of the word. And I knew they were. In fact, this was pointed out recently by a post I made and by a video that you uploaded showing that they actually went back on their word to give us as much time as we needed to get what we needed to say out there. And so they were kind of trying to rush through the evidence. And it was funny because they basically wanted me to explain how we know the Earth is round, how we know the distance to the sun, how we know how fast we're going around it, and how we know that we're the ones that are spinning and not the universe around us, all within a 15-minute time frame. They were asking for the impossible. And they basically wanted me to sum everything up in one argument. There is no one size fits all equation to literally everything. There is none. You have to look at each problem on its own merits and each equation on its own merits, and then you have to align the merits with another compatible merit. And so if we look at it that way and we understand that each problem is unique, we also find that each solution is unique. And so you need to go over each question individually. You can't simply jump into it and expect a one size fits all answer. It's not going to happen. You're asking for the impossible. And when you go over multiple points, you need the time to actually get it all out there. And after I did my presentation, after Ziller did his presentation, even though we were interrupted, we had over 90 minutes worth of us getting everything out there, and they still were rushing us. Where if you look at the original post made on Skype, they promised us as much time as possible. And in fact, they looked at the more time we spent as a good thing and then went back on their word as the show was halfway through. So, but I do thank you for giving me the platform and being so friendly and welcoming. It's good to see that.
Yeah, we're not all crazy in the conspiracy community.
Well, that's good. That's good. That's what I like to hear.
Yep. I want to encourage the listeners, this is exactly what it takes to get to the truth. You can't just make up your mind and then argue till you're blue in the face. You have to hear each other out. You have to listen to other people's perspectives. And if they say something that contradicts what you think you owe it to yourself to go off and research that thing and delve into it and see if there's any merit to it.
Absolutely agree. Absolutely agree. And again, if you want to go and find all the links that I posted, I will make a Dropbox folder that has all the diagrams that I used. I'll put them in there so that you can go over them yourself, the people that are watching, that you can go over yourself, look at them. And if you want to kind of follow along with this broadcast, it'll kind of make it easier for you. That way, if there's something that you don't understand or something that you have a question about, you can go back to that slide, send me a PM, and I'll be more than happy to go over it with you.
Fantastic. Alrighty, well, Red, thank you again. It's been an absolute pleasure. Do you want to pimp out your channel here a little bit?
Sure. Again, my name is Red. I run the YouTube channel Reds Rhetoric. It's basically me and my rhetoric. And it's not only that, there's also some rocket launches in there, which I highly recommend people go see. One of them explodes. So if you want to subscribe to my channel, I'm sure my channel will be listed down below in the description. And just be warned, I'm not as free of profanity as I was in this broadcast. There is quite a lot of it. So understand what you're getting yourself into when you decide to click on my videos. Any small children, send them out or put on the earmuffs.
Yes. Okay. Well, thank you guys. Thank you so much for listening. If you haven't already, please like and subscribe. Thanks. Thank you again, Red. And God bless.